Welcome! In this focus, we will explore how the food supply chain contributes to greenhouse gas emissions and what factors make the biggest impact. People worldwide are increasingly worried about climate change. 8 in 10 see it as a major threat to their country. In 13 of 26 surveyed nations, climate change is viewed as the top global threat. Concern is especially high in Greece, South Korea, France, Spain and Mexico, where at least 80% see it as a major threat. In contrast, only 59% of Americans consider climate change a serious threat. Across countries, a median of 20% view climate change as a minor threat, and 90% say it is a not threat at all. In Israel and Russia, about half or more share this view, while in the US 23% call it a minor threat and 60% say it is not a threat. In addition, concern about climate change has increased significantly since 2013. Then a median of 56% in 23 countries, so it is a major threat. Now the figure has risen to 67%. In 10 countries, concern has grown by at least 10 percentage points. For example, in France, from 54% to 83%. When addressing climate change, attention is often directed toward clean energy solutions, such as expanding renewable or nuclear power, improving energy efficiency, and shifting to low-carbon transport. This emphasis is understandable, as energy use in electricity generation, heating, transport, and industry account for the majority, around 76% of global greenhouse gases emissions. However, the global food system, including both agricultural production and post-farm activities like processing and distribution, is also a major source of emissions. Agriculture plays a dual role. It is significantly contribute to climate change while also being one of the sectors most vulnerable to its impact. Emissions from on-farm production, that is within the farm boundaries, and related land use change make up 20–25% of total human-generated emissions. This contribution becomes even more notable when considering specific gases. Crop and livestock activities within farms produce over half of methane and about 3/4 of nitrous oxide emission worldwide. When emissions from pre- and post-production processes, including fertilizer, manufacture, food transport, processing, retail, and waste management are added, the total impact grows substantially. Estimates suggest that the entire food system is responsible for between 20% and 40% of all human-caused GHG emissions, with recent analysis placing the figure at 1/3. This significant contribution underscores the potential of mitigation strategies focused on food systems, encouraging innovation across supply chains, consumption habits, and waste management alongside farm and landscape level actions. Likewise, it is increasingly recognized that dietary habits and consumption patterns are crucial levels for lowering food-related emissions due to their influence on production and supply. Food production is a key component of the agricultural sector and is responsible for about 26% of global greenhouse gas emissions. The food supply chain is composed of several stages, from farming to the final consumer. Each link in this chain plays an essential role and contributes to emission in different ways. In fact, every stage can be associated with specific emission sources. Identifying these sources is crucial to assess the total emission generated by a product throughout its supply chain. In this regard, there is a paper by Poor and Nemchek that tried to quantify the environmental impact of a food product through a life cycle analysis approach. This method evaluates impact across multiple stages of the supply chain. The study in particular assesses emissions from a cradle-to-gate perspective, which include land use change, on-farm impact from crop and livestock production, including the manufacturing of inputs such as fertilizer and emissions from manure. Include also animal feed production, feed processing, meaning the transformation of raw materials into finished product, for example, processing cereals into bread. Transport, covering movement from the farm to retail, but not from retail to consumers' homes. And then packaging, activities that occur after the retail stage, such as home cooking, refrigeration, or household food waste, are not included in the assessment. In this survey, authors identified 1,530 studies for potential inclusion, in addition to additional data from 139 authors to supplement these. Then assessed the studies on basis of 11 criteria to make sure that the methodologies used in each were standardized. For example, making sure that all stages of the supply chain were considered. After this assessment, they had 570 suitable studies which used a consistent and high-quality methodology. Their final dataset covered approximately 38,700 commercially viable farms across 119 countries. It spanned a total of 40 food products, which represent approximately 90% of global protein and calorie intake. With the data collected from the study, it was possible made the graph that we can see in this slide. The visualization shows GHG emissions from 20 non-food products, from beef at the top to nuts at the bottom. For each product, you can see from which stage in the supply chain its emission originate. These extend from land use changes on the left to transport and packaging on the right. In this comparison, we look at the total GHG emission per kilogram of a food product. Carbon dioxide is the most important greenhouse gas, but not the only one. Agriculture is a large source of the greenhouse gases methane and nitrous oxide. To capture all GHG emissions from food production, researchers express them in kilograms of carbon dioxide equivalents. This metric takes into account not just carbon dioxide but all greenhouse gases. In Chapter 2 is present a focus on this topic. Overall, animal-based food tend to have a greater environmental impact than the plant-based ones. For instance, both lamb and cheese emit over 20 kilograms of carbon dioxide equivalent per kilogram of product. Poultry and pork produce lower emissions at around 6 and 7 kilograms of carbon dioxide equivalent per kilogram, respectively, but their footprints still exceed those of mass plant-based food. In particular, animal feed represents a minor share of emissions from poultry and pork production. When it comes to dairy products, cheese has a much larger carbon footprint than milk when measured per kilogram. This is because cheese is essentially a concentrated form of milk with much less water content. However, when comparing the two on the basis of protein or caloric content, their footprints become more similar, since cheese contains higher levels of both protein and energy per kilogram. For the majority of foods, especially those with the highest emission levels, the bulk of greenhouse gas emissions come from land use change in green and activities occurring during the farm stage in brown. The impact of land use is about the deforestation below ground and changes in soil carbon. Emissions generated on farms stem from practices such as applying fertilizer, both organic, manure management, and synthetic, as well as from enteric fermentation, the process by which cattle produce methane during the digestion, that have high pollution power than carbon dioxide. If you want more about this, Chapter 2 provides information on the main source of pollution and their pollution power. Together, land use change and farm activities make up over 18% of the total emission footprint for most types of food. From the graph, transportation contributes only a small fraction to overall emissions. For the majority of food items, it represents less than 10% of total emission, and its share is even lower for the highest emitting food. For instance, just 0.5% for beef from cattle herds. In cane sugar and bananas, however, the transport is the mass emission source. Moreover, not only transport, but also other post-farm supply chain activities, such as processing, packaging, retail, and distribution, generally make up only a minor portion of total greenhouse gas emissions. Emissions are lower especially for sea transport, that is also the most common, and rail transport. However, for air transport, the emissions are extremely high, roughly 50 times greater per ton kilometer than shipping by sea. Air-freighted foods are usually highly perishable, meaning they must be consumed shortly after harvest. For these items, slow transport by sea isn't feasible, so air travel is necessary. Common examples include fruit and vegetables, like asparagus, green beans, and berries. It can be difficult for consumers to know which products were transported by air, as they are rarely labeled. A useful guideline is to avoid food with very short shelf lives that have traveled long distances. Labels indicating the country of origin can help. A study case on the American orange reports that varying the transportation mode of oranges delivered to Atlanta, Chicago, Los Angeles, and New York City has greater potential for reducing the carbon footprint of oranges than eating locally or seasonally. This is largely attributable to the fact that produce shipped from greater distances is more likely to travel via relatively efficient mode, for example container ship, than a relatively inefficient mode as for example truck. The same conclusion can be drawn for animal-based food. Transport emissions are a small fraction of the total animal-based food emission. For most animal products, the majority of greenhouse gas emissions come from production, for example, enteric fermentation, manure, feed production, and not from transport. Local sourcing reduces transport emissions, but the overall climate benefit is often minor compared to production emissions. Production emissions vary greatly by region. In some cases, importing animal products from regions with more efficient, lower emission production systems can result in lower total greenhouse gas emission than consuming locally produced but less efficient animal products. For ruminant livestock, for example beef or lamb, production emissions are so high that transport emissions, even for long distance, are relatively insignificant in the total footprint. In addition to the previously discussed supply chain stages, food loss and waste represent a significant contributor to greenhouse gas emissions. Food waste and loss occur at every stage of the supply chain, consistently representing a loss of both resources and associated emissions. In 2015, global food loss waste generated 9.3 gigatons of dioxide carbon equivalents through supply chain activities and waste management systems, accounting for roughly half of the total annual GHG emissions from the entire food system. According with one study, in fruit supply chain, food loss, transportation, packaging and production contribute 36% to 88%, 90% respectively to the total emission on average. Food loss waste emissions arise from multiple sources across 9 post-farm stages and vary depending on country, region and food category. Factors such as income level, technological availability, and dietary patterns also influence regional and national food loss waste emissions. Strategies to reduce food loss waste related emissions include halving food loss waste generation, reducing meat consumption, and improving waste management technologies. In the figure, we can see an example of a Sankey diagram for the production and food loss of 1 kg of cherry. The life cycle food losses for 1 unit of produced cherries are 66. That means, for example, that 50% of cherries will be lost on the farm after 1 kilo was produced. Then 8% of the remaining cherries will be lost during transportation from farm to retail, followed by an additional loss of 10% in retail and about 50% in the consumer's home. Therefore, of the original 1 kilo of cherries produced, only about 34% will be eaten. It is important to emphasize that emissions from the food supply chain are not the only factor used to describe the environmental impact of the entire system. The environmental footprint of food production is evaluated through a combination of criteria, mainly greenhouse gas emissions, land use, water consumption, and eutrophication, assessed using life cycle and composite indicator approaches. Soil degradation is also a relevant aspect to consider. In conclusion, the environmental impact of the food system goes far beyond greenhouse gas emission alone. A full assessment must consider multiple factors, including land use, water consumption, eutrophication, soil degradation, and abiotic depletion, across all stages of the supply chain, from farming to waste management. Each step contributes to total emission, and food loss and waste represent a major share of this impact, accounting for nearly half of all food-related GHG emissions. When it comes to individual choices, transportation plays only a minor role in mass food footprints, except for those transported by air. Most important emission source as the production of food, especially in animal-based one. To reduce your diet carbon footprint, it helps to avoid air-freighted food where possible. However, the biggest difference comes from what you eat, rather than where it comes from. Eating less meat and dairy or replacing ruminant meat with poultry, pork, or plant-based alternatives can lead to much larger emissions reductions.